Today I'm going to talk about Minterm and Maxterm. Maxterm. Let's assume we have an AND gate and it has some inputs and one output. A, a specific combination of the input gives the output of 1. Okay, so we call this particular configuration of inputs that yield to 1 at the output a minterm. So a minterm is a particular and combination of the variables that yield to 1 if a variables are passed through an AND gate. So let me write it down. So a minterm is that particular and combination of the variables that yield a 1 if the variables are passed through an AND gate. Let's see. For example, when a as a variable is 0, b is 1, and c is 0. Okay, so what is like the corresponding minterm of these variables? We should find the combination of these variables which yield to 1 if these variables are applied to the AND gate. We know that if we apply A, B, C as is like this to an AND gate, the output is 0 because A and C are 0, and the output of an AND gate is 1 only and only if all inputs are 1. So which combination of these variables should be applied to the input so we get 1 at the output? So A is 0. So let's apply A bar. If A is 0, of course A bar is 1. So A bar is 1 input. What about B? B is 1. So we apply B to the input. What about C? C is 0. Let's apply C bar because if C is 0, C bar is 1. So the minterm here, the corresponding minterm is A bar, B, C bar. If we apply A bar, B, C bar to an AND gate, the output will be equal to 1. Okay, so for this example, when A is 0, B is 1, and C is 0, then the corresponding minterm is, as we discussed, is A bar, B, C bar. Okay, since A bar, B, C bar would yield a 1. Okay, so this one is minterm. What is maxterm? Maxterm, in fact, is the opposite of the minterm. It's an all combination of the variables that if we apply to a OR gate gives the output is 0. So if we have an OR gate like this and inputs, what combination of the inputs should be applied to the gate so the output is 0? This combination is called Maxterm. Be careful, for Minterm we have AND gate, for Maxterm we have OR gate. Okay, so first let's write the definition of Maxterm. We know that Maxterm is the OR combination of the variables that gives a 0 if the variables are passed through an OR gate. Okay, for example, if A is 0, B is 1, and C is 0, then before writing the answer, let's see which combinations of A, B, and C should be applied to OR gate, so like in a way that the output is 0. So if we apply A, B, C, of course because B is 1, the output will be 1, because based on the truth table of OR gate, we know that if any of the inputs, at least one input is 1, the output is 1. So here, because B is 1, output will be 1. So in order to have the output of 0, we apply A, because A is 0, we apply A. B is 1, so we apply B bar. When B is 1, B bar is 0. And C is 0, so we apply C. So the Maxterm is A plus B bar plus C. Okay, since A plus B bar plus C would yield a 0. Why here I say A plus B bar plus C, but for Minterm I say A bar B C bar, because here we applying to all gates, so we show it like with like dot, or we show it with like a multiplication. It's not a mathematical multiplication, it's like and. But for Maxterm, because they are applied to all gate, we show their combination by plus sign. Okay, so based on this definition, we see that in fact Maxterm is complement of the Minterm, and of course vice versa. Okay, so let's see one example. We have this function f of a b, which, and we want to write Minterms and Maxterms. Okay, so it's a b Minterm and Maxterm. A and B have 4 different combinations for the minterm. Let's first start writing minterm. For minterm, we show them with lowercase m. Lowercase m stands for minterm, uppercase m stands for maxterm. So we have four minterms, m0, m0, m1, m2, m3. M0, which combination of A and B here should be applied to yield a 1? Of course, because both of them are 0, we know that A bar, B bar yield a 1. M1, A is 0, so we say A bar, B is 1, we keep B. M2, A is 1, we say A, B is 0, we say B bar. M3, A and B both are 1, so we simply say the minterm is AB. Now max terms, M0, M1, M2, M3. Which combination of A and B should be applied to, or it can be applied to OR gate, so yield a 0. Because A and B both are 0, we can say A and B gives a 0. It's a max term. M1, A is 0, so we keep A for max term. B is 1, we complement B. A is 1, we complement A plus B. And finally, both of them are 1, so we should write them in the form of complement. Okay, so this one is minterm and max term of this function. Okay, now that we know what are the minterm and max terms, we want to start a new topic which represent the different functions. We have two forms of representing or showing function. We can represent the functions in the form of a sum of product or in the form of a product of sum. Okay, let's discuss these two forms. The first one is sum of product. Or we can show it with SOP form. Sum of product, don't forget, in fact, is sum of minterms. Okay? So, a function f can be represented by an expression that is a sum of minterms. So we can represent any function with the like sum of minterms. Sum of like a product or some of these minterms can be obtained by ORing. ORing means like all those functions, ORing the minterms. Let me just write the definition of sum of products, and then we see examples. A function, let's say function f, can be represented by an expression that is a sum of minterms, as I mentioned. Sum of product form can be obtained by ORing the minterms that cause the output to be a 1. Okay, this part is very important. Owing the minterms that cause the output to be 1. So we should pick those minterms that cause the output of the function to be 1. Okay, let's see one example. We want to represent the following function in in sum of product form. Okay, the function is given in the form of truth table. So here is the function. It's x1, x2, and f of x1 and x2. Okay, so 0 0 0 1 1 0 1 1, and the output is 1 0 0 1, and we want to show or represent this function in form of a sum of product. The first thing we should do here is expanding the table and write the minterms. The minterms, of course, m0 is equal to x1 bar, x2 bar. m1 is equal to x1 bar, x2. m2 is equal to x1, x2 bar. m3 is equal to x1, x2. Okay, we have all minterms. So which of these minterms causes the output of the function to be 1? So these two, you see, the output of the functions, the output of the function is 1 for these two combinations. So we pick those minterms. So these minterms cause like the output of 1, and we can say the function is equal to m0 plus m3. m0, or we can show it in this form, the sigma of m0 and 3. We have this representation as well, which is equal to x1 bar, x2 bar plus x1, x2. So we at this point we represented the function in the form of sum of minterms. Okay, sum of the minterms. Okay, so before moving to the next like part, which is product of sum, I want to introduce a new definition, which is a canonical sum of product. What is a canonical sum of product? Canonical sum of product. We call a sum of product canonical if each product term is a minterm. For example, f of a, b, c is a bar b, c plus a, b bar, c plus a bar, b, c bar. If we look to any of these products, we see that all of them are a minterm, sorry. All of them are minterm. So we say this function is canonical. Let's show one example which is non-canonical. Let's say we have this function f of a, b, c. We know that sum of products, so we should have some products that we all them together. So if these products are like this, a bar bc plus bc plus abc. If we look to this function, we see that this one is a minterm. This one is a minterm. How do we know? Because they contain all the variables a, b, and c. The third one has all the variables A, B, C. But the middle one has only B and C. It doesn't have A. So it's not a minterm. Because the second product is not a minterm, we say that this function is non-canonical. Okay? Because the middle function, the middle term BC is not a minterm. It doesn't have all variables. So we conclude that the function is non-canonical. Okay, so let's move to the next part, which is a product of some form, or POS form. The POS, or product of sum, also can be called as product of Maxterm. Okay, so product of sum is obtained by ANDing the Maxterms corresponding to the zero output. Be careful, for minterms we always want to reach to output 1. For Maxterms we want to reach to output 0. So product of sum is obtained by ANDing the Maxterms corresponding to the 0 output. Okay, so it's exactly a complement of minterm. So let's see one example. Represent following function in POS form, product of sum. Here is the function x1, x2, f of x1 and x2. 0, 0, 0, 1, 1, 0, 1, 1, and 1, 0, 0, 1. Okay, in order to solve this problem, we expand the truth table and write the max terms. M0 is x1 plus x2. M1 is x1 plus x2 bar. M2 is x1 bar plus x2, and M3 is x1 bar plus x2 bar. Okay, so we should pick those max terms that yields like causes a 0 in the output. So we should pick M1 and M2. So we can say the function is M1, M2, product of these two max terms. For min terms, we say lowercase m plus lowercase other m, but here we multiply them because it's product of these sums. So also like the sigma of min terms that we showed for min term, we can use this sign to show the multiplication or product of some max terms. So the product of max term 1 and 2, which is equal to, of course, x1 plus x2 bar and x1 bar plus x2. So now we represented this function in the form of a product of sum. If we look to these two functions, to the output of this function and the previous example, we see that both of them are same. Because both of them are same, the function should be same. So we conclude that this form of the representing the function is exactly same as this function. So these two functions are same but represented in a different way, but they are exactly same. Let me show it. Okay, let me just try to see if we can prove it. So uh, for function x1 x2 in the form of product of sum, which I said is equal to max term 1 and 2, which is equal to x1 plus x2 bar times x1 bar plus x2. Let's multiply these two parentheses together to see what we get in the output. So it's equal to x1 bar plus x1 x2 plus x2 bar x1 bar plus x2 bar x2. So this term is 0, this term is 0, and it will, what we will have, it's x1 x2 plus x2 bar x1 bar. And if we look to this representation 4, we see that it is exactly the sigma of min term 0 and 3. Okay, so it's exactly same as sum of product. Okay, so in the other word, if I say the function in the form of so the previous one was the function in the form of product of sum, and if I write the same function in the sum of product form, it's equal to sigma min term 0 and 3, which is equal to x1 x2 plus x1 bar x2 bar. If we look, we see that this one is exactly the same, this one. So sum of product representation is exactly the same as product of sum representation. Okay, so now we saw a canonical sum of product. What about canonical product of sum? So canonical product of sum. When do we have a canonical product of sum? When each term is a max term. Okay, so for example, we have this function f of abc, which is A bar plus B plus C, A plus B bar plus C bar. So it's function 1. We have another function f2 of A, B, C, which is equal to A bar plus B plus C, A plus B bar. If we look to these two functions, we see that for the f1, both the like sums are Maxterm, but for the second function, this first term is Maxterm, but second term is not a Maxterm, not a Maxterm. How do we know it's not a Maxterm? Because it doesn't include all the variables. So we can say this one is canonical form, this one is not canonical form. Okay, so now that we learned the Minterm and Maxterm, we want to see one design example which we use Minterm and Maxterm concept to design the circuit. Okay, so we are going to discuss a design example. Okay, we want to design a voting machine that accepts three inputs. Let's call them A, B, and C. The circuit is to output 1, to output like a 1, to output a 1, when a majority of the inputs are 1, except when A and B are 1 and C is a 0. Realize this voting machine in sum of product form and product of sum form. Okay, so we have a voting machine with three inputs A, B, and C, which like has an output of 1 when the majority of inputs are 1, except one condition, and that condition is when A and B are 1 and C is 0, the output is 0. And we want to represent this or design this voting machine in two forms, in the form of sum of product and product of sum. The first thing we should like do when we are going to design a problem or design a circuit, it's finding the truth table of that circuit. So now it's time to write the truth table of this function. Okay, so here is the truth table of the function. We have three inputs and we have output. Input A, input B, input C. How many different combinations do we have for three inputs? Of course, 2 to the power of 3, which is 8. So the inputs are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These are 8 possible combinations. What about the output? We say the output is 1 when the majority of the outputs are 1. So when all three inputs are 0, the output is 0. When only C is 1, the output is 0. When only B is 1, the output is 0. When B and C are 1, the output is 1. When A is 1, the output is 0. When A and C are 1, the output is 1. When A and B are 1 and C is 0. This one is like a special case that we mentioned in the problem. We said that except except when A and B are 1 and C is 0. So here it was supposed to be 1, but the problem mentions that if C is 0 and A and B are 1, output is still 0, and if all of them are 1, the output is 1. Okay, so we got the output. And now we write minterms and maxterms. Minterm. First, let's write minterms. Start from M0. M0 is A bar, B bar, C bar. M1 is equal to A bar, B bar, C. M2 is equal to A bar, B, C bar. M3 is equal to A bar, B, C. M4 is equal to A, B bar, C bar. M5 is equal to A, B bar, C. M6 is equal to A, B bar, no, A, B, C bar. And M7, of course, is equal to A, B, C. Now let's write the maxterms. Capital M0 is equal to A plus B plus C. M1 is equal to A plus B plus C bar. M2 is equal to A plus B bar plus C. M3 is equal to A plus B bar plus C bar. M4 is equal to A bar plus B plus C. M5 is equal to A bar plus B plus C bar. M6 is equal to A bar plus B bar plus C. And finally, M7 is equal to A bar plus B bar plus C bar. Okay, we got to this point, and now it's time to write the functions. What we did so far, we wrote the truth table, and now we are supposed to write the sum of product. Okay, so we say that canonical sum of product is equal to f of a, b, c is equal to sigma of minterms. Which minterms? Minterms which causes output 1. So this minterm, and this minterm. So minterms 3, 5, and 7, which can be written in this form: a bar b c plus a b bar c plus a b c. This one is the canonical form of product sum of product. Let's write the canonical form. Just leave some space here. We need it later. Canonical form of product of sum. So we should look to max terms which causes 0 in the output. So which max terms? This max term, this max term, this max term, this max term, this max term. By the way, let's have a question here. At this moment, we can answer to a simple question. Should we go with minterm to design this circuit or maxterm? If we look here, we see that the number of terms for the minterm is less than number of terms for the maxterm. So definitely the answer is it's better to go with minterm to design this circuit because it has less terms and of course less cost, less number of gates, and faster. Okay, so let's just design in both forms. Max terms, the canonical form of max terms, f of a, b, c is the product of max terms 0, 1, 2, 4, and 6, which is equal to a plus b plus c, a plus b plus c bar, a plus b bar plus c, a bar plus b plus c, and a bar plus b bar plus c. Okay. So we want to design these two circuits, this one and this one. By the way, the problem doesn't say anything about being canonical. So it says that design the circuit. So let's see if we can simplify these circuits. For sure, we cannot simplify this product of sum because it has like so many multiplication are involved in this form, so we cannot simplify this it in a like easy way. But for sum of product, we can do some simplification. So what we do, let's just simply factor out b and bc from first term and second term. So bc, we factor out bc, so we will have a bar plus a plus a b bar c, which is equal to a plus a bar is 1. It's equal to bc plus a b bar c. Let's factor out c. C is equal to b plus a b bar. Okay, law of elimination, it's equal to c a plus b, which is equal to ac plus bc. Okay, one thing which is important, this function is exactly same as this function, it's exactly same as this function. All of them are same. Okay, so this one is in form of product of sum, yeah. These two, this one and this one, are in the sum of product. One of them is canonical, the other one is non-canonical. But because the problem doesn't say about anything about being canonical, it's better to design the circuit with the simple version, which is non-canonical. Or let's design all three circuits. Okay, I'm going to show all these three circuits. Okay, so first, sum of product. First one is sum of product canonical. The circuit is in this form. We will have A, B, C, these wires. Of course, we need the complement of these variables as well. So let's just have the complement of these variables. Okay. So here we have C bar, here we have B bar, and here we have A bar. We put an AND gate here, which says A bar. Don't forget this, like small circles to indicate the connections. So if you see these wires, it's only connected to this line, not the other lines. Okay, so A bar, BC. So BC. I'm looking to this function. Let me show you here. A bar, BC. And I just connected them together. So here is A bar, BC. The next one I need to design is AB bar C. AB bar C. So let's again add another AB bar C. So we get A, B bar, and C. This one is the second one. The third term is in the ABC in canonical form. ABC. So we want to get ABC. So we get A from A, B from B, and C from C. So we got these three terms, and we should OR them together. We put OR gate here and all these three functions together. And here is f of a, b, c. This one is like a design for first design for the voting machine. Now I want to show again sum of product, but this time non-canonical. Okay, non-canonical. For non-canonical, it's easy. What do we have? We have only C times A plus B or AC plus BC. So we have A, C, and we have B, C. We OR them together, and function is f of A, B, C. So this one is a second design. You see how simple is this non-canonical design compared to the canonical. Okay, so the last design is the same function in the form of product of sum form. Product of sum form. Okay, so we need to build all these 5 terms one by one and then AND them together. Let's do that. Here is A, here is B, here is C. We complement all these variables. Okay. Uh, First term is A plus B plus C. So we get A, we get B, we get C, and it's A, B, C. Where did I bring it? Here. Okay. The next one is A plus B plus C bar. A plus B plus C bar. So we get A, we get B, we get C bar. The next one is A plus B bar plus C. So we get A, we get B bar, we get C. The next one is A bar plus B plus C. So we get A bar. Let's extend this lines. We get A bar, we get B, and we get C. And finally, the last one is A bar plus B bar plus C. So we get A bar, B bar, and C. Now we have like the max terms. We need to AND them together with a 5-input AND gate. So first one, second one, third one, fourth one, and fifth one. And so it's F of A, B, C. So this one is the design. So you can now compare all these three designs together to see which one is like better, it costs less, and it's faster. Of course, the winner of this competition is non-canonical sum of product. Okay, thank you for paying attention to this lecture. We will continue our discussion on midterms in the next lecture.